Hey guys, we are starting exponential functions today. This is section 3.1. You should remember some of this from last year, but let's go through them anyway. First, exponential functions are power functions in which the base is the constant and the exponent is a variable. So until now, we were used to seeing functions such as, f of x is x squared. Now, in exponential functions, the 2 will be the base and the variable will be the exponent. Okay? The most important thing to remember about exponential functions is first, they all have asymptotes and they increase rapidly. So, whatever you can think of, like population, number of bacteria in a culture, and so on, all these follow exponential growth or decay patterns. All right, let's just dive right in. What are some examples of exponential functions? As you see here, you have 3 to the x. You might have something like 1/2 to the x. There might be some constant in the front of that as well. Or it could be e to the x, e to the x minus 1, and so on. Right. Let's talk about some properties of exponential functions. Here we have 2 graphs. The first one is for exponential growth. And let's just take a look at what the trends of that look like. So first of all, this function has, or this graph rather, has a horizontal asymptote. That means here, right, it follows that asymptotic behavior. And then as you can see, as your x values increase, this graph increases, but it increases very, very rapidly. The best place to see that is, higher up in the x values. So if you see here, if this is 1 x value, if I just go over a tiny bit in the x values, right? So if this is x1, this would be the y value, y1. And now if I just go over a tiny bit in my x value, right? Let's see where I end up, right here, okay? Look at that. Look at that value of y2. So look at how much more the y values increased compared to how little the x value increased. So that's, the biggest characteristic of exponential functions is that there is a very large growth in the y value for a very small increase in the x value. All right. The domain of all exponential functions is all real numbers, because if y is, let's say, 3 to the x can take on any value, right? There is no value of x that would make it undefined. The range, as you see here in this particular one, is 0 to infinity. So basically what it is it starts from the horizontal asymptote and will either go up or down. And what I also want you to pay attention to here is that the end behavior, one end will go to 0, right? So here, the end behavior is 0, and the other end will be infinity. So again, one end will follow the horizontal asymptote, whereas the other end will go to infinity. And they're continuous everywhere. Right, so this is an example of exponential growth, and you see as your x values increase, so do the y values. That would be, for example, if a population is increasing. We could also have situations of exponential decay, in which case we start at a higher value, and then as time goes on, the amount or the value in question will decrease. All right, this is called exponential decay. Again, you've got a horizontal asymptote, same as before. And again, there is a rapid change in the y value, this time in the negative direction because it decreases. Radioactive decay is an example, and so on. So they follow the same trends, but one increases and the other decreases. Okay, again, domain is all real numbers, range is very similar. Again, end behavior, one end will be at infinity and the other end will level off at the horizontal asymptote. In this case, it's 0. In another case, it might be something else. Okay. So that's how you can tell if a function is growth or decay based on a graph. And we'll talk a little bit more about that in a little bit. But what if you only have a function to look at? Well, let's take a look at that. A function, an exponential function, is defined as f of x equals b to the x. More generally speaking, it might be f of x equals a constant a times b to the x. In either case, you've got this constant b raised to the exponent. And the function is said to be exponential growth if that number b is greater than 1, and it's exponential decay if that number b is between 0 and 1. All right, so take a look at these examples, and let's classify the following as exponential growth or exponential decay. All right, in the first case, I have 2 to the x. The only thing I look at is that 2. Who does the exponent belong to? The 2. Since 2 is greater than 1, it's growth. Here I have 0.5 to the x. All right, 0.5 is between 0 and 1. That's decay. This one is also decay because of the 1/3. Now, suppose there was a 2 out front here. Right? And if it was f of x is equal to 2 times 1/3 to the x, nothing would change because you ask yourself, who does the x belong to? It belongs to the 1/3. That's between 0 and 1. We're good to go. Okay, this one, I have a 1/4 to the negative x. So your first instinct might be to say that it's decay, but that negative x, remember, makes the 1/4 into its reciprocal. So that changes to 4/1 to the power of x. And then you see that it's clearly growth and not decay. All right, let's do some graphing. We're going to graph a very basic 2 to the x. Let's start with the asymptote. The default asymptote for these, if there is no vertical shift, is y equals 0. That's the horizontal asymptote. All right, the y-intercept, I want us here to get used to the notation for function notation. So we're going to say f of 0 is 2 to the 0. You plug in 0 for x. That's 1. So the y-intercept is f of 0 is equal to 1. All right, to graph, I like to pick points. All right, now 2 to the x is growth. For growth, I generally like to pick -1 to 2 for my x values. Is that a rule? It's not. It's merely my preference. But I find that these values generally tend to give the most manageable values for y, right? These things increase so rapidly that you don't want to have numbers that get out of hand too quickly. So these are the ones that I like to pick most of the time. All right, so here we're going to get 2 to the -1, 1/2, 2 to the 0, 2 to the 1, 2 to the 2. And let's graph. First, I put up the asymptote, and then I just put up my points. All right, so starting at x equals -1, we have a value of 1/2, 1, that was my y-intercept, 2, and then 4. And now I want to graph my exponential function. So let's be careful here. This is not a graph. This is connect the dots, and it was fine back in kindergarten. But now, since this is an exponential function, we need to show the two characteristics. A, that it increases rapidly, and B, that it follows that asymptote to the end. All right, cool. Domain, there is no reason to think about it. For all exponential functions, it's all real numbers. Range is either going to be y is greater than or less than the asymptote. The asymptote was at 0. Since this is sitting on top of the asymptote, it's greater than. End behavior. As x approaches negative infinity, the limit is 0. Positive infinity, it's infinity. And it's continuous everywhere. All right. So, as far as the range, if this is a positive, right, if there is a positive coefficient in front, the range is going to be y is greater than 0. If there was a negative coefficient, the range would have been y is less than 0, or the asymptote. Okay, take a look at this one. The asymptote again is y equals 0. Y-intercept, f of 0 is 1. Okay, this is dk. For dk, I like to shift my numbers and just start from -2 to 1. Again, most of the time these are fabulous. So let's go. This is 9, 3 to the 1, 3 to the 0, 3 to the -1. All right, let's put up the asymptote. At -2, y is 9. At -1, it's 3. 0 and 1/3 for x equals 1. And that's how it looks. And that's dk. Okay, domain is all real numbers. Range is the same. This time, as x approaches negative infinity, limit is infinity, and 0 on the other end, and it's continuous everywhere. All right. Let's talk about transformations. All right, so same rules apply. If this function here, the blue one, is my original function, 2 to the x. If I have 2 to the x plus 1, I take the x plus 1, set it equal to 0. X is -1, so there is a shift in the negative direction of 1 unit. So that's a horizontal reflection. A horizontal translation, I'm sorry. All right, now, here, look at this one. I have 2 to the x. Now that's a growth, right? That's a growth. Now if I change it to 2 to the -x, right? We can look at it in 2 different ways. First, the fact that x is negative, that negative makes it a reflection around the y-axis. But also in the case of exponential functions, y equals 2 to the -x is now dk, right? Because 2 to the -x is 1 over 2 to the power of x, right? So it's not only a reflection around the y-axis, it actually changes it from exponential growth to exponential decay. And you see how the graph mimics that very, very well. All right. Next, here I have 2 to the x. And now if the coefficient in front becomes a negative, now it's a reflection around the x-axis. Okay. So now here is the question. This is now -3 2 to the x. Look at the equation. This is still an equation for growth, okay? And now look at the graph. Most students will look at this red graph and say, oh, it's going down, it's decreasing, it must be decay. No, this is still grows.